In today's video, we're going to be talking about related rates, but before we go into all the stuff I've drawn on the board, I need to make a couple things clear. First of all, we'll be using something that looks like this quite a lot. This is dx dt, and it looks very similar to how we represent derivative notation. Essentially what this is saying is we want to find the derivative of x with respect to time. And I need you to understand that before we go into this whole lesson. This can be true for y, it can be true for r, it can be true for v, whatever variable we want to use. Okay, now let's talk about this whole mess that I've made up here on the board. When we talk about related rates, we want to find the rate of change of one thing relative to another thing changing. In our first problem, we have Gary here at the top of a 10-meter tall ladder. Morgan is pulling the ladder away from the wall at 0.5 meters per second. And what we want to find out is how fast is Gary falling in meters per second when the ladder is now 6 meters away from the wall. There's a couple things we're going to need to find out first before we dive into this problem. First of all, we need to find out this length, aka the height of the ladder when the ladder is 6 meters away from the wall. So before we go too far, let's denote some things. Y is equal to the distance between the ladder and the floor. And x is the distance between, by the way, B/W stands for between, distance between the wall and the base of the ladder. And one thing that's really nice of this problem is that the length of this ladder doesn't change, so we don't have another weird variable within our problem. And the other nice thing about this problem is that this ladder forms a triangle, a right triangle to be exact, with the wall and the base, which means that we can use Pythagorean theorem to find this y length here. Let's do that now before we dive too much further into the problem. Remember, the Pythagorean theorem states that a squared plus b squared is equal to c squared. So let's plug in our a and b. A will be 6, so 6 squared, plus y squared is equal to our c, also known as our hypotenuse, which is 10 squared. So now we have the problem 36, 6 squared is 36, plus y squared is equal to 100, aka 10 squared. To solve for y squared, you need to subtract 36 from both sides. So this turns into y squared is equal to 64, and square rooting both of these sides, we get that y is equal to 8. So this y value is equal to 8 meters. I know that looks a little weird, but 8 meters. And now that we have the height between the top of the ladder and the floor, we can solve this problem. I'm just erasing a couple things here so I have plenty of room to work with. It turns out the actual word problem itself takes up a lot of space. So here's how we're going to start it. First of all, we're going to make x and y be functions with respect to t, aka time. So dx dt represents x with respect to time, or the change in x with respect to time. And dy dt represents the same thing, but with, well, y. And from the word problem, we also know that dx dt equals 1/2, aka 0.5, right here. That is how fast x is changing with respect to time. X is increasing by 0.5 meters per second. So our job in this problem is to find dy dt. We are looking for the change in y with respect to time, which we don't know yet based on this problem, because the change in y with respect to t is the same thing as our downward speed. So here's how we apply dx dt and dy dt to our problem. We just talked about how this forms a right triangle, which allows us to use the Pythagorean theorem, aka x squared, the base, plus y squared, the height between the top of the ladder and the base, is equal to 10 squared, which is the length of the ladder, which never changes. Now here's something very important to understand about derivatives. When we take the derivative of a position function, such as x squared plus y squared, d dt, d dt, the derivative of a position function, such as x squared plus y squared, is equal to the velocity function. This is something that comes up in physics quite often. Basically, if you take the derivative of your position function, you'll get the function that tells you how fast an object is changing over time. So if I had a graph that told me the change in speed of my car over time, if we took the derivative of that function, it would tell me how fast my car is going over time. And that's essentially what we're doing here. So let's apply the derivative to both of these functions. The derivative of x squared is equal to 2x dx dt. Remember, we're taking this function with respect to time, so we're going to tack on this dx dt to it. The derivative of y squared is equal to 2y. Remember, both of these are just the power rule. We take this 2 to the front and subtract 1 from the exponents. And here we're going to tack on a dy dt. The derivative of a constant, such as 10 squared, is just equal to 100, is 0. So now we're starting to get somewhere, but what's our next step? So this is the function we had just a minute ago, and I want to simplify this down just a little bit. As you can see, we can divide everything by 2. So whenever we divide everything by 2, our new equation turns into x dx dt plus y dy dt equals 0. And now we need to isolate for dy dt. Remember, the whole point of this problem is we're trying to find the change in y given the change in x. And dy dt represents that change in y. So let's isolate for dy dt. First of all, we can subtract x dx dt over to our right side. So now this equation turns into y dy dt is equal to x, or negative x dx dt. Now the last thing to do in order to isolate for our dy dt is divide by y on both sides. So our final equation, which is going to be up here, dy dt is equal to negative x divided by y dx dt. And now we can use this equation in order to find the change in y over time, aka how fast our little man Gary is falling. I hope he's okay, because that is a long fall and very scary. What are you doing, Morgan? Okay, so remember earlier when we talked about the Pythagorean theorem, how 6 squared plus 8 squared is equal to 10 squared, which we proved earlier to find that y, this value, is equal to 8. Well, we also know that x is equal to 6. We already had that given to us in the problem, and we can use this in order to solve the problem. So our change in y with respect to time, aka dy dt, is equal to negative x divided by y times dx dt. And, well, we know x and we know y. So this is equal to negative 6 divided by 8 times dx dt, aka the change in x over time, which is 0.5 meters per second. So this is just multiplied by 1/2. Negative 6 times 1 is equal to negative 6. 8 times 2 is equal to 16. So our final answer is dy dt is equal to negative 6 divided by 16, which can be simplified down to negative 3 divided by 8 meters per second. Negative 3/8 meters per second is how fast Gary is falling relative to how fast the ladder is being pulled out. So now that we solved this question, I want to talk about the steps to solve any related rates question, and then do one more with some different types of numbers and different formulas. So I'm going to erase this and then talk about the steps. So here I've now written the usual steps you take in any given related rates problem and rewritten our problem over here. I know it doesn't look quite as nice, but it is rewritten with all the steps. Our first step is to draw a picture. The picture I had up before we started the lesson was of Gary on the ladder getting pulled that way. It gave us an idea of how these relationships could be interacting with each other and helped us get a good starting base. And you're going to want to do this on any related rate problem, as it makes it a little bit easier to solve and much easier to visualize. We also established a relationship between x, y, and our 10-meter ladder that was given to us, which is actually step 2, find a relationship. We found that all three of these lengths were related via the Pythagorean theorem, since this triangle was formed by the ladder, the wall, and the base. This also helped us figure out that y was equal to 8 in order to help us solve this problem. The third step is to use implicit differentiation, which I already did a lesson on. If you want more in-depth guidance to implicit differentiation, you can check out the link over there. We established that dx dt is equal to the change in x with respect to time, and dy dt is the change in y with respect to time. By the way, delta x and delta y mean the change in that variable, and the w with the slash is width. So since we knew the relationship between these three lengths was the Pythagorean theorem, we could write out our equation as such. We used implicit differentiation since we had our y variable within the equation in order to solve it. This led us to solve the equation, eventually leading us to dy dt is equal to negative x dx divided by y dt. All we had to do then was plug in numbers. Our x was equal to 6, so negative 6 divided by 8, our y value, times 1/2, which was our dx dt, or our change in x with respect to time, since the ladder was being pulled at 0.5 meters per second. That led us to find our final answer of the change in y, aka how fast Gary is falling, to be negative 3/8 meters per second. We're going to do one more problem. I just wanted to show you the general steps for any related rates problem here. And this problem is not going to use ladders or triangles at all. In fact, we're going to be using spheres. I know. Crazy. Okay, in our second and final example for this video, we have a balloon that's being pumped up at a rate of 3 inches cubed per second. We want to find out how fast the radius of this balloon is increasing when the radius is equal to 2 inches. Now we have a couple key pieces of information here that we need to identify. First of all, the volume of this balloon is increasing at 3 inches cubed per second. That will come very handy later on, and I even wrote it over here. Second, we need to know how fast the balloon is expanding when the radius of said balloon is 2 inches. So we're going to use V to represent volume, and we'll use r to represent radius. And dr dt represents the radius of the balloon with respect to time, aka how fast is the radius increasing at some given point. And we're looking for that dr dt when r is equal to 2 inches. So let's see if we can find a relationship between the radius and the volume of the balloon. Well, let's assume that this balloon is a sphere. and the volume of a sphere is equal to 4/3 times pi times the radius cubed. Hey, would you look at that? We have a bit of a relationship going here. Let's run with that. This is also a formula that you may want to know in case you do run into a balloon type related rates problem, so be sure to remember that the volume of a sphere is equal to 4/3 pi r cubed. So based on this volume equation for a sphere, we can use that to find the rate of change of that volume given the formula. So let's write that down over here. So we're looking for d dt, aka the derivative with respect to time, of v, our volume, and that all equals to 4/3 pi radius cubed. And since we're finding the derivative of this side, we also need to find the derivative of this side. So to simplify this down, the derivative of v is just dv dt, which represents the volume with respect to time, aka the change in volume with respect to time. In this problem, we need to take the derivative of r. Using the power rule, we bring this 3 to the front and then subtract 1. Notice when we bring the 3 to the front, it becomes a coefficient, so this and this 3 will cancel out. So then this equals 4 pi, and then subtracting 1 from our power, we get r squared dr dt, because we took the derivative of r with respect to t. Now we have an implicit differentiation problem that we can work with. First of all, we know that dv dt is equal to 3 inches cubed per second. This is the change in volume given time. So I should probably write this down over here. This is equal to dv dt. So we can actually just replace dv dt with 3 inches cubed per second. Since we replace dv dt with a number, we can also replace r with a number. So this is now equal to 4 times pi times our radius, which is 2 inches, squared dr dt. And yes, it is very important to keep your units in these problems, especially this one. It'll come up later, I promise it makes sense. So let's simplify this problem down. First of all, we can square this side, so this now equals 3 inches cubed per second is now equal to 4 pi times 4 inches squared. Remember, we have to apply the square to the unit as well, times dr dt. Now 4 times 4 is equal to 16, so we may as well simplify that as well. 3 inches cubed per second is equal to 16 pi inches squared times dr dt, which remember is just our change in radius with respect to time. And actually, well, I mean, we're looking for our change in radius with respect to time, so we just need to isolate that variable now. And the easiest way to do that, simply divide by 16 pi inches squared. And of course, we need to do that on both sides, 16 pi inches squared. We're going to cancel out this inches squared and cancel out 2 of these to just be 1, and then our seconds just remains as it is. So now our equation turns into 3 divided by 16 pi inches per second is equal to dr dt. And this is, well, our final answer. We found that whenever the volume of the sphere is changing by 3 inches cubed per second, when our radius is 2 inches, the radius of that balloon is increasing by 3 divided by 16 pi inches per second, aka dr dt, and we just solved the problem. And we even have the right units. That's why we kept the units on the whole time. We definitely want to keep those there to verify that our answer is correct, because if our units were wrong, then we did something wrong in the process. So that's related rates when it comes to something spherical, so be sure to remember that the volume of a sphere is equal to 4/3 pi r cubed. And that's all I got for you guys today. I hope you guys found this video helpful, as related rates can be a bit of a confusing topic for Calculus 1 students. If you want more Calculus 1 videos, check out the playlist here, and I'll see you guys in the next lesson.